Dear children, myself Bindu Verma will be discussing the remaining portion of the chapter solution. The solution chapter is divided into two portions. The solution part and the second part is colligative properties of dilute solution. The solution part already you have studied. So I'll be teaching you colligative properties of dilute solutions. Before teaching colligative properties of dilute solution, I'll just discuss once more Raoult's law for binary solution containing two volatile miscible liquids. Raoult's law for a binary solution containing two volatile miscible liquids. Now, in this the word volatile, you know the meaning of volatile? It's what which vaporizes easily. Vaporizes easily, why? Because the intermolecular force of attraction is very weak. Miscible means they'll mix with each other, but they does not undergo a chemical reaction to give you a new compound. So now let us take two volatile liquids. One is normal hexane and the other one I'm going to take is N-heptane or normal heptane. A known mass of hexane is taken and a known mass of heptane is also taken. So we know the molar mass of hexane, we know the molar mass of heptane. So we can find out the mole fraction of hexane, which I am going to denote it as X1, and mole fraction of heptane as X2. Now we are going to find out experimentally the vapor pressure of N-hexane and N-heptane, which we can do it in the laboratory. But at present I can't do, just we are imagining we are performing the experiment. And we are going to do the experiment at a constant temperature of say 300 Kelvin. So we are finding out the vapor pressure of normal hexane and I'm going to denote it as P1 naught and of N-heptane as P2 naught. So we know the mole fraction of hexane and we know the mole fraction of heptane. We know both vapor pressure also. Now I am going to plot a graph with mole fraction along the x-axis and vapor pressure along the y-axis. Now we have plotted a graph with mole fraction along the x-axis and vapor pressure along the y-axis. Now see in this graph, on the left side I have written x1 is equal to 1, x2 is equal to 0. Here x1 is 0 and x2 is equal to 1. And we have taken what type of solution? Binary solution. And already you have studied the total mole fraction of a solution is always equal to what? Tell me it will be what? It's unity. So what can you write? x1 plus x2 is equal to 1. So here you have x1 is equal to 1 and x2 is equal to 0. Why? Because normal hexane is in which form? Pure form. That means here you have got only component normal hexane. And here x1 is 0 and x2 is equal to what? 1. That means here you have got which component? Normal heptane. So you don't have component 1. Pure component is present. Now you see, I am just going to explain you the graph. Now here x1 is 0. So what is the vapor pressure of component 1 also? That is also 0, that is hexane. Its vapor pressure is 0. Slowly what is happening to the mole fraction? As we move towards the left, it is increasing. So what is happening to its vapor pressure also? It is also increasing. So it slowly increases, reaches the extreme left where the mole fraction becomes equal to 1 and the vapor pressure becomes what? Maximum. That is P1 naught. So what can you say? When mole fraction is increasing, the vapor pressure is also increasing. Now next you see for component 2 also, here the mole fraction on the left side is 0. So when we move towards the right side, what is happening to the mole fraction? It is increasing. So what is happening to its vapor pressure also? It is also increasing and reaches to a maximum when the mole fraction is what? 1. And we have done this at a constant temperature. We haven't changed the temperature also. So what can you say? When mole fraction is increasing, the vapor pressure of a component in solution is also increasing. Now the same thing I am going to explain it another way also. See here, when the mole fraction of component 1 is 1, its vapor pressure is maximum, that is P1 naught. That this represents the pure vapor pressure of component 1. Why? Because the component 1 is not in contact with another component. And you see this graph, when it goes towards the right, what is happening to the vapor pressure of component 1? It is decreasing. Why is it decreasing? Because it is coming in contact with component 2. So what happens to the escaping tendency of component 1? It decreases because the surface is also occupied by what? Component 2. So its vapor pressure is decreasing. Got it? So the vapor pressure of component 1 decreases as it comes in contact with component 2. So this P1, we can call it as partial pressure of component 1. Similarly, you see, when the mole fraction of component 2 is 1, its vapor pressure is also maximum. And when it comes towards the left side, what is happening to its vapor pressure? It is decreasing. Why? It's coming in contact with component 2. So P2 is known as partial pressure or vapor pressure of partial vapor pressure of component 2. So from this graph, what can you say? Mole fraction when increases, the partial vapor pressure is also increasing. So from this it is clear that the partial vapor pressure of a volatile component is directly proportional to its mole fraction. That is, when mole fraction of component 1 is increasing, its partial vapor pressure is also increasing. Similarly, partial vapor pressure of component 2 is also directly proportional to its mole fraction. So this is the definition for what? Raoult's law. When you have a binary solution containing two volatile miscible liquids, that is, the partial vapor pressure of each component in the binary solution is directly proportional to its mole fraction. So P1 proportional x1, P2 proportional x2. So P1 is proportional to x1, P2 proportional to x2. Now, in order to remove this proportionality sign, I am going to multiply it by the pure vapor pressure. Why I am multiplying it with the pure vapor pressure? Why? Because the pure vapor pressure of a pure component always remains constant at a particular temperature. So you'll get P1 is equal to P1 naught x1, P2 is equal to P2 naught x2. So understood the definition for Raoult's law? When you have got two volatile miscible liquids, the partial vapor pressure of each component is directly proportional to its mole fraction, or you can also define it as the partial vapor pressure of a component is the product of pure vapor pressure of that component multiplied by its mole fraction. Now, we know P solution or P total is equal to P1 plus P2, which you have already studied last year in Dalton's theory, Dalton's law of partial pressure. That is, total pressure is the sum of the partial pressure of all the components present in the solution. So we can write here P total is equal to P1 plus P2, or P total is equal to P1 naught x1 plus P2 naught x2. Now, x1 plus x2 is equal to 1. So you can express the mole fraction either with respect to 1 or component 2. I am just going to express it. Mole fraction of component 1 is equal to 1 minus x2. Why I am going to take it this way, I will explain later. So you'll get P total is equal to P1 naught into 1 minus x2 plus P2 naught x2, or P total equal to P1 naught minus P1 naught x2 plus P2 naught x2. Or you can write what? x2 you can take it as common. x2 into P2 naught minus P1 naught plus P1 naught. So this is the expression for total vapor pressure of the solution. So I have taken here x1 is equal to 1 minus x2 instead of taking x2 is equal to 1 minus x1. See this graph. You see both the solutions, do they have the same pure vapor pressure? No, the component 2's vapor pressure is greater than the vapor pressure of component 1. So that is the reason I have expressed the mole fraction of component 1 with respect to component 2. So the equation has become P total is equal to x2 into P2 naught minus P1 naught plus P1 naught. Suppose if the vapor pressure of component 1 was greater than that of component 2, then the expression would have been what? P total is equal to x1 into P1 naught minus P2 naught plus P2 naught. So this is the expression for total vapor pressure. So is it clear? Raoult's law, that Raoult stated that the partial vapor pressure of each component in a binary solution containing two volatile liquids is directly proportional to mole fraction. So when mole fraction increases, the partial vapor pressure also will increase. So with this concept only, we'll be doing some numericals. Okay. So for doing numericals, the equations which you are going to use are as follows. I'll just write it on the board. Now for doing numericals related to Raoult's law, the equations which you'll be using is P1 is equal to P1 naught x1, P2 is equal to P2 naught x2, P total is equal to P1 naught x1 plus P2 naught x2. Or you can use this equation also. P total is equal to P1 naught plus x2 into P2 naught minus P1 naught. Okay. This equation, see, P1 is equal to P1 naught x1, P2 is equal to P2 naught x2. This will be used to find the mole fraction of constituents or components in liquid phase. Okay. Now in the question sometimes you'll get to find out the mole fraction of components in vapor phase. To find out the mole fraction of components in vapor phase, you can't use this equation. In that case, you will be using the equation which you have studied in class 11th in the chapter states of matter, that is using Dalton's law of partial pressure. Hope you people remember the equation. What is the equation? P1 is equal to Y1 into P total, P2 is equal to Y2 into P total. Here Y1 and Y2 are actually what? Mole fraction of the same component, that is 1 and 2, but it's in which state? Vapor phase. It's in vapor phase. So to find out the mole fraction of the components in liquid phase, you can use this equation. And to find out the vapor pressure, the mole fraction of the components in vapor phase, you have to use this equation. So now we will discuss a numerical related to Raoult's law. Okay. So let us do a numerical related to Raoult's law. See, methanol and ethanol form an ideal solution. It is prepared by mixing 32 gram of methanol and 23 gram of ethanol at 300 Kelvin. At 300 Kelvin, the vapor pressure of pure methanol and ethanol are 90 mm of mercury and 51 mm of mercury respectively. Calculate the partial vapor pressure of its constituents and total vapor pressure of the solution and mole fraction of each component in vapor phase. So they have given two components, methanol and ethanol, and it is prepared by mixing 32. So I am going to do what, I'm just going to divide it into two portions. In one portion I am going to write it as methanol, and another portion I am going to just write it as ethanol. Then what all quantities are given to you in the question, that will write it. So let us take methanol as component 1 and ethanol as component 2. So methanol's mass is given. So W1 I am just going to write it as 32 gram. Ethanol's mass is also given. W2 is equal to 23 gram. Then molar mass of methanol, it also comes to be 32 gram per mole, and that of ethanol comes to be 46 gram per mole. The next is the pure vapor pressure of methanol is given, P1 naught, 90 mm of mercury, and that of ethanol also is given, P2 naught is equal to 51 mm of mercury. So it's clearly given that 32 gram of methanol is mixed with 23 gram of ethanol at 300 Kelvin, and the pure vapor pressure of methanol and ethanol is given. Methanol is given 90 mm of mercury and ethanol is given 51 mm of mercury. And they are asking you to find out the mole fraction of the components. So you have to find out x1 and x2. So now how will you find out x1? x1 is equal to W1 by M1 by W1 by M1 plus W2 by M2. So it comes to be 32 by 32 plus 23 by 46. So which will be equal to 1 by 1 plus 1 by 2. So that will be equal to 2 by 3. So this is the mole fraction of component 1. So if you have got the mole fraction of component 1, the mole fraction of component 2 easily you can find out. 1 minus x1. So it will be how much? 1 minus 2 by 3. So it will be 1 by 3. So you have got the mole fraction of component 1 and component 2. So that is asked in which phase it is? In liquid phase. Next they have asked you to calculate the total vapor pressure of the solution. To calculate the total vapor pressure, you are going to use the equation P total is equal to P1 naught x1 plus P2 naught x2. So what is P1? P1 is equal to P1 naught x1. So it comes to be 90 into 2 by 3. So how much it will come? 60 mm of mercury. Then P2 is equal to P2 naught x2. So it comes to be 51 into 1 by 3. So it comes to be how much? 17 mm of mercury. So what will be the total pressure? P total is equal to 60 plus 17, that is 77 mm of mercury. So this is the total vapor pressure of the solution. So it's clear. So the first part of the equation is over, that is partial vapor mole fraction of each components, then partial vapor pressure of each components, and then the total vapor pressure of the solution. Now we have to calculate the mole fraction in vapor phase. So the equation you are going to use is P1 is equal to Y1 into P total. So P1 is how much? 60 equal to Y1, and P total is how much? 77. So 60 divided by 77 is equal to Y1. So Y1 approximately it will come to be 0.78. So when you have got Y1, Y2 you can calculate. Y2 will be equal to how much? 1 minus Y1. So that is 1 minus 0.78. So which comes to be 0.22. So you have to be very careful when a question is given, whether they are asking you to calculate the mole fraction in liquid phase or in vapor phase. For liquid phase, you can use the equation P1 naught x1 or P2 naught X2. And for vapor phase, you can't use that equation. You have to use the equation given by Dalton's theory, that is P1 is equal to Y1 into P total and P2 is equal to Y2 into P total. You can't use the same equation for liquid phase and vapor phase, because for Raoult's law's equation we are using only for liquid phase, and Dalton's equation we are using it for vapor phase. So now we'll go to the next topic, that is colligative properties. Next we'll study is colligative properties for dilute solution. It's very important topic because to all dilute solutions follow this colligative properties. So what is colligative property? It is the property of a dilute solution which depends upon the amount of non-volatile solute added in the solution and does not depend upon the nature of the non-volatile solute. So that is known as colligative property. The property which depends upon the amount of non-volatile solute which we are adding in the solution and not depending upon the nature of the non-volatile solute. So what can you say? Colligative property is directly proportional to amount of non-volatile solute. It is not depending upon the nature of the solute, whether it's a solid or a liquid, or whether it's an electrolyte or a non-electrolyte, or it's in a molecular state. Whatever way it's state, it doesn't depend, it just depends upon how much of solute you are adding. Just I'll give you a simple example. Now here I am taking a beaker. In this I am taking say 100 molecules of A. In another beaker, I am taking B, say 50 moles of an electrolyte. Another one I am taking say 120 molecules of a non-electrolyte. So here you have got 100 molecules of polar molecules, here 50 moles of electrolytes and 120 molecules of non-electrolytes. So on the basis of the definition, which will have the highest colligative property? Because colligative property depends upon what? Amount of non-volatile solute. So here you have got 100. In B you have got 50 and in C you have got 120. So on the basis of the definition, the beaker C will be having the maximum colligative property. Why? Because the number of molecules are more. So colligative property is the property which depends upon the amount of non-volatile solute which we are adding, and it's not depending upon the nature of the solute. So the 4 colligative properties which we have to study this year are as follows. One is relative lowering of vapor pressure. The second one is elevation of boiling point. And the third one is depression in freezing point. And the last one is osmotic pressure. So the 4 colligative properties which we'll be dealing in this chapter are: 1 is relative lowering of vapor pressure, 2 is elevation of boiling point, 3 is depression in freezing point, and 4 osmotic pressure. So all these 4 colligative properties, they will depend upon only what? The amount of non-volatile solute which we are adding in the solution. It won't depend upon the nature of the non-volatile solute which we are adding. So now we'll discuss relative lowering of vapor pressure. Now let us consider let us prepare a solution by mixing a non-volatile solute in a volatile solvent. Okay. Let the non-volatile solute be component 2 and the solvent be component 1. So already you have studied when we add a non-volatile solute to a pure volatile solvent, the vapor pressure of the solvent decreases. Why the vapor pressure of the solvent decreases? Because the non-volatile solute will not vaporize and it will occupy the surface, some of the surface occupied by the solvent molecules. So the escaping tendency of the solvent molecule decreases. So here you see, we know P total is equal to P1 plus P2. P1 is the partial vapor pressure of solvent and P2 is the partial vapor pressure of non-volatile solute. Now the non-volatile solute is not vaporizing. So what will be P2 equal to? P2 is equal to 0. So P total is equal to P1. So the total vapor pressure of the solution is equal to the vapor pressure of what? The solvent. Hence we can write P1 is equal to P1 naught x1 and we know x1 plus x2 is equal to 1 or x1 is equal to 1 minus x2. So in this equation you can write P1 is equal to P1 naught into 1 minus x2 or P1 is equal to P1 naught minus P1 naught x2 or P1 naught x2 is equal to P1 naught minus P1 or x2 is equal to P1 naught minus P1 by P1 naught. So x2 represents what? The mole fraction of the non-volatile solute. P1 naught represents the pure vapor pressure of the solvent. P1 represents the partial vapor pressure of the solvent. So what have we done? We have prepared a solution by mixing a non-volatile solute in a volatile solvent. And already we have studied that when a non-volatile solute is added to a volatile solvent, the vapor pressure of the solvent decreases because some of the surface will be occupied by what? Non-volatile solute, and the non-volatile solute will not vaporize. So its partial vapor pressure will be always what? 0, and even its pure vapor pressure also will be 0. So the total vapor pressure of the solution will be equal to the vapor pressure of the solvent. So on that basis we have done this derivation, and finally what are you getting? The mole fraction of the non-volatile solute is equal to P1 naught minus P1 by P1 naught, and this quantity P1 naught minus P1 by P1 naught is known as relative lowering of vapor pressure. Relative lowering of vapor pressure. So what can we write? The mole fraction of the non-volatile solute is equal to relative lowering of vapor pressure. So this is also the definition of Raoult's law when the solute is non-volatile. So Raoult had performed experiment both with volatile solute as well as non-volatile. So according to Raoult's law, when the solute is non-volatile, its mole fraction is equal to what? Relative lowering of vapor pressure. Now this quantity P1 naught minus P1 by P1 naught, which is known as relative lowering of vapor pressure, is a colligative property. Is a colligative property because it does not depend upon the nature of the non-volatile solute. But the quantity P1 naught minus P1, which is known as lowering of vapor pressure, is not a colligative property. P1 naught minus P1, which is known as lowering of vapor pressure, is not a colligative property. P1 naught minus P1 by P1 naught, which is relative lowering of vapor pressure, it's a colligative property. So today we have dealt with colligative property. It's the property of dilute solution. So that you have to keep in mind. Colligative property is the property of dilute solution, which depends upon only the amount of solute and not the nature of the solute. And the four colligative properties are relative lowering of vapor pressure, elevation of boiling point, depression in freezing point, and osmotic pressure. So we just studied relative lowering of vapor pressure, and we have from that derived the definition for Raoult's law when the solute is non-volatile. That is, when the solute is non-volatile, the mole fraction of the non-volatile solute is equal to relative lowering of vapor pressure. So the remaining colligative properties will be continuing in the next class.